Hello everyone and welcome back to LFI Educates. We are in the fifth video today with this chapter, current electricity. Here you need to learn some 2-3 new terms again. Here I have written the first one, the electromotive force. We represent with this symbol epsilon, and in short we write it as EMF also. This indicates electromotive force. For a cell to maintain a steady current across the circuit, suppose this is your cell, to maintain a steady current, say I, across the circuit, it needs to do some work. The cell needs to do some work. This work done in moving a unit positive charge throughout the whole circuit, including the cell, inside the electrolyte of the cell as well. We call it as EMF, or we call it as electromotive force. Here the SI unit of EMF is also same as that of potential. We write it as volt. And electromotive force epsilon can also be written as the work done in bringing unit positive charge. So this way we can represent electromotive force. Now the second term that we are going to learn is internal resistance. Internal resistance of the cell. We write it as small r. Internal resistance, when we say inside the cell between the electrodes, positive and negative, this one is your positive terminal, this is your negative terminal, you have electrolyte. This electrolyte also offers some resistance inside the cell. That resistance we generally call it as internal resistance of the cell. Sometimes we denote it with this symbol and we write it as small letter R. Or sometimes in some circuit, if you don't want to write here, you can represent in one side like this. It will indicate R. And the EMF of the cell will write as epsilon. And then the resistance outside, this is your bulb or your fan or your TV set, whatever it is, that is your external resistance. We write it as R. Now the third thing that you have to know is here the SI unit of internal resistance is also ohm. Like your internal resistance, external resistance units are the same. And the third term that you learn today is terminal potential difference. Let me write it as V. Terminal potential difference is the difference in potential between the two terminals of the cell when the circuit is closed. That means when the current starts flowing in the circuit, then the difference in potential between these 2 points will be called as terminal potential difference. Now this terminal potential difference is always less than the EMF of the cell by this factor I into R. Here this is also the potential, but the potential inside the cell. This internal resistance will offer, the internal resistance is present in the electrolyte. So the current that flows from one end to the other end of the cell will be offered, the resistor will offer the resistance, and then a small potential will be developed inside the cell. That we write it as I into R. But when the circuit is open, if the circuit is open circuit, this one the switch is open here, current is not flowing. In that case, the current I will be equal to 0 and the EMF of the cell and the potential will remain the same. The EMF and the potential will remain equal. Now let us see a very important relation that exists between the electromotive force, that is your epsilon, total internal resistance R, and terminal potential difference V. Relation between electromotive force, the internal resistance small r, and the terminal potential difference V. Now here, let us assume like this, let the external resistance be R, or you can start like this, let a cell of EMF epsilon whose internal resistance is R and R is the external resistance also let I be the current flowing in the circuit when the circuit is closed. Let us assume like this. In the initial stage, when the circuit is open, as I said earlier, when the circuit is open, that means when there is no current flowing in the circuit, I is equal to 0 and your EMF is equal to the total terminal potential difference. So I will be equal to 0 and EMF will be equal to the potential difference. But when the circuit is closed, the current flowing through the external resistance R, you can find out like this: current I is equal to the EMF of the cell divided by the sum of the two resistances, internal as well as external. Let me mark this equation number 1. But here the symbol for EMF, we are taking it as epsilon. Now, we know by Ohm's law current I is equal to V by R. When in Ohm's law, we don't take into account the EMF of the cell. Then in that case, the current flowing through this resistance, if you take in terms of terminal potential difference, then we write I is equal to V by R. Let us take this as equation number 2. By combining these two expressions from equation 1 and 2, we can get like this: V by R is equal to epsilon divided by R plus R. As the left hand sides are equal, the right hand sides also will be equal. Now if you cross multiply it, you will get like this: VR plus VR, and multiplying with terminal potential difference and this one external and internal resistance, VR plus VR is equal to epsilon r, epsilon r. So we need this small r. So what we'll do is Vr will keep on left hand side, epsilon r minus Vr. So you can take here epsilon minus V and r you can take common here. Then bring down this V, epsilon minus V divided by V into r. This gives us the relationship between these three physical quantities: the internal resistance, the EMF of the cell, the potential, as well as the external resistance. So this one we can rewrite like this: R is equal to epsilon by V, this one separated, minus V by V will become 1 into R. So this gives us the relationship between these three physical quantities: internal resistance, EMF, and terminal potential difference. Let us do one numerical and see. The reading on a high resistance voltmeter, this is a voltmeter, when a cell is connected across it, is 2.2 volt. When a cell is connected across it, the potential is 2.2 volt. When the terminals of the cell are connected to a resistance of 5 ohm, when the terminals are connected to a resistance of 5 ohm as shown, the voltmeter reading drops to 1.8 volt. As soon as this resistance is connected, the voltmeter drops to 1.8 volt. By looking these two values, you can make out very clearly this is the EMF of the cell, and as the potential drop, the potential becomes less. That is the terminal potential difference, that is V, and the external resistance is given as 5 ohm. From here you are asked to find out the internal resistance of the cell, which you cannot see in the diagram, but you should know that there is one internal resistance of the cell. You can draw outside as well as you can draw here as well. Like this you have to think. Now, to find out the internal resistance of the cell, the factors for that you know is given that EMF is 2.2 volt, the potential, terminal potential difference is 1.8 volt, and the external resistance R is equal to 5 ohm. So with these values, we can calculate. We know that we can calculate the internal resistance R with the formula EMF of the cell divided by terminal potential difference minus 1 into external resistance R. So simply we have to put the values and then we have to calculate it. The EMF is 2.2 volt, it's 1.8 minus 1 into external resistance is 5 ohm. So this one, after decimal 1 digit, you can remove it. You can write 11 by 9 times, 2 9s are 18, 2 11s are 22, minus 1 into 5. So if you take the LCM, 9, 11 minus 9 into 5, 2 divided by 9 into 5, this will be 10 divided by 9, and the unit of resistance is ohm. So we'll write here ohm. Like this you can calculate the internal resistance of a cell if you know the external resistance, the EMF, and the terminal potential difference. Now let us learn about two very important laws given by Kirchhoff. The laws, we call them as Kirchhoff's laws. Kirchhoff's laws. It is divided into two parts. The first part is the first law, follows the law of conservation of charge that we have learned in the first chapter. This is also known as Kirchhoff's current law. The net current across a junction, suppose this is I1, this is I2, this is I3, this is I4, this is I5. The algebraic sum of all the currents meeting at a point is 0. So I'll write on the law, the algebraic sum of all the currents meeting at a point is 0. So the charges, the flow of current is the flow of charge. It will always remain conserved. Here what you do is, if you do the net sum, we use sign convention. Coming current in towards the junction, this is the junction, we take it as positive, and going away from it we take it as negative. So if you do like this, I1 plus I2 minus I3 minus I4 minus I5 is equal to 0. I3, I4 and I5, the currents are going away from it. That's why I took it as minus. And this I1 and I2 is coming towards it, so I took it as plus. This law you can understand this way also. I1 and I2, they were coming in, that will be equal to I3 plus I4 plus I5. That means how much current is entering the junction, the same amount of current should leave the junction. That way also you can understand it. The another way of understanding is, suppose I1 is 5 ampere. Suppose this is 5 ampere. This is 6 ampere. Total is 11 ampere. So leaving also it must be 11. Let us say I3 is 2 ampere. I4 is 5 ampere. Together it becomes 7. And how much remaining to get 11? 4. So I5 from there 4 ampere will leave. Suppose I1 and I2 is 5 ampere and 6 ampere. Total is 11. So leaving also should be 11. This is what it says. This is Kirchhoff's first law. We call it as Kirchhoff's current law as well. Let us see the second law. Kirchhoff's second law. This is also known as KVL. This is Kirchhoff's voltage law also we say. And this law is applicable in a closed circuit. There is one circuit you can see. I have drawn and kept in advance. Now in this case, the law says like this: the algebraic sum of all the potential differences in a closed circuit is always 0. Is always 0. Let us understand this law by taking this circuit diagram. Just I have drawn one circuit diagram with resistors R1, R2, R3 and R4. And I have marked the rectangle as A, B, C, E. Then at this cell I took this point as D. At this resistance, let this point be F. Then you can see the direction of current also. Suppose you know which side is flowing. It may flow this direction, it may flow this direction. It's up to you, and according to the question how it will come. But now here you need to learn the law, how to deal with it. To explain this second law, that is Kirchhoff's voltage law, I have drawn one circuit here. You can see 2 cells are there and 4 resistances, R1, R2, R3 and R4. The current directions are also given. You can see I1, I2, I3, I4. Which direction to flow, it will be given in the circuit. Now to understand this law, what we do is we select a path A, B, C, D, E, A, or A, E, C, B, A. Any way you can choose it. Where you want to start, you can start. Suppose I am choosing from A to B. This is the path the current is flowing, or the path I have chosen from A to B. And what I'll do is potential at A and potential at B. It will give us the potential difference VA minus VB. Current is in the same direction as I have chosen the path, so I'll take it as positive. It will be IR1, product of current and resistance. That will also give us the potential difference across the resistor. Now I'll choose from B to C the path as I'm coming down like this. B to C, if I do, then I'll write VB minus VC. Here, same thing again, current and is in the same direction with that of the path and the current are in the same direction. So I am taking it as positive, that is I2 R2. Then here we have divided into two parts. The path from C to E, I made it as CD and then DE. Let us do part by part. There is one EMF here. C to D, when I take, it will be VC minus VD. That is equal to the terminal here is coming from negative to positive. Instead of going from positive to negative, it is going from negative to positive. So there will be potential drop. So potential drop, we will write it as minus then epsilon 1. Then from D to E, when I take VD minus VE, then again we have current and resistance in the same direction, so it will be positive, plus that is I3 R3. Then we'll come here. Here also I have divided into two parts, E to F and F to A, because in F to A you have one EMF or one cell. So this is your path. So it is in the opposite direction. Current is in the opposite direction. So automatically it will be negative VE minus VF will give us negative of the potential I4 R4. And then from F to A, if I go, from VF to VA, if I go, then you can see here there is no potential drop, there is gain potential, it is going up from positive to negative. So I'll take it as positive. So I'll take it as plus epsilon 2. Like this, you can find out the potentials at all the points A to B, B to C, C to E, E to A. After this is done, you can sum them up. If you sum up, then you get like this. Left hand side you can see here VA plus VA minus VA will be 0, minus VB plus VB minus VC plus VC, like that. All the terms will get cancelled each other. So ultimately the left hand side everything is 0. On the right hand side you will get I1 R1 plus I2 R2 minus epsilon 1 plus I3 R3 minus I4 R4 plus epsilon 2. This one you can even write it as epsilon 1 minus will become plus on your left hand side when you transpose it, minus epsilon 2 is equal to I1 R1 plus I2 R2 plus I3 R3 minus will become plus I4 R4. So in other words, we can even say that the algebraic sum of the EMFs, here is the algebraic sum. So it depends upon the direction of the polarity of the cells. E1, I am taking it positive. When you look the circuit, when you apply Kirchhoff's law, you are not going to do like this, but this also you have to know. When you apply Kirchhoff's law in a closed loop, you will see this positive terminal. So you can draw like this. This is anti-clockwise. Anti-clockwise, we are taking it as negative. Anti-clockwise, we take it as negative. So E2 is negative, minus E2 or epsilon 2. And this one, if you look, E1, this is the positive terminal, so according to us, this should be the direction of current for this cell. So it is clockwise, we take it as positive, epsilon 1, that's why it is positive. That is equal to, in case of current and resistance, the product, you can take this one, this way it is going, that means it is forming clockwise. So positive, I1 is positive. This one is coming like this, so this is also clockwise, so positive. This one I3, this is also going like this, so it will be showing this side, this is the closed path. You will take it this way, clockwise, so positive. But this one showing downside means you will think like it is anti-clockwise and you will take it as negative. Here one term should be negative, this is minus. Sorry, this one must be minus. So while doing the numericals for Kirchhoff's law, you can follow this and you can do it anti-clockwise, negative, and clockwise, this will take it as positive. So Kirchhoff's voltage law can even be written like this also. The algebraic sum of the EMFs is equal to the algebraic sum of the products of current and resistances in a closed loop. Let us do one numerical and see. Let us make it more clear. Let us solve this question and see. You have to find the currents in different branches of the electric circuit shown in the figure. Here the branches currents are given, I1, I2, I3, how it is flowing. The circuit diagram is given to you. What you have to do is you have to find out what are the currents that are flowing in the circuit. I1 coming in the branch here, getting separated, I2 and I3. Then this I3 flows this way. Then here I2 comes this way. They meet in the junction. I1 and I2 and I3, if they meet here, then total current will become I1. Again it will flow and reach up to the, and will complete the circuit. So let us use this Kirchhoff's laws. Here first of all, I1 is the sum of I2 and I3. So you will use Kirchhoff's current law using KCL. Kirchhoff's current law. This is the first law. We can write I1 is equal to I2 plus I3. Let us mark this as equation number 1. Then let us go to the loops. There are two loops you can see here, A, B, E, F and B, C, D, E, B. This one, second one. One by one we shall do it. Let us take the first loop. Using Kirchhoff's voltage law, the second law, in the loop A, B, E, F, A, A, B, E, F, A, we can write down the sum of EMFs. Let us do the sum of EMFs. How to do? This is the first EMF. Positive terminal is on the top. That means it is flowing this way. This is clockwise. Clockwise we take it as positive. 2 I write plus. Forget about this second loop. Think in the first loop. Look the first loop. And then this second cell, positive terminal is down. Then this is the loop. The current flows from positive side this way. So this is also clockwise. So we'll take it as positive. That is equal to the sum of the products of current and resistances. Now multiply current and resistance. Whatever resistance you see, there is one resistance. Then this arrowhead is showing this way. That means if this is the loop, current is going in the clockwise direction. So this also will be positive. I1, 4I1. Then the next one, here there is no resistance, so we won't take I2. Here you have one resistance. So this one, how the current is flowing? This way. Then you will take it this side. This is also clockwise. So this is 2I1 plus 2I1. Like this you complete the law. Use the law. Then here 4 plus 2 is 6I1 equal to 2 plus 4 is 6. So I1 is equal to 6 by 6 is 1. So it is 1 ampere. Like this you can find out the current. Likewise again use the second loop. Again using KVL in the loop. Your loop name you can give it how you want to take it, clockwise or anti-clockwise. B, C, D, E, B. Let us take B, C, D, E, B. And again we will use some of the EMFs on the left hand side. Here, first EMF is this one, suppose I have chosen. This one I have taken the second one. This current will flow this direction. So it is anti-clockwise. Anti-clockwise, then negative will come, -4 plus. This one positive is this side. So current will flow in this direction in the loop. So this is also anti-clockwise. So I will take it as minus. How much it is? 6 volt. That is equal to again product of current and resistances. This is going this way. The current is flowing this way, going like this. So it is positive 2I3. 2I3. Then here current and resistance going like this. Means this is the loop. So it will go this way clockwise. This is also positive 4I3 plus 4I3. So it will become 6I3 and this is minus 10. So I3 is equal to minus 10 by 6. This is 2 3s are 6, 2 5s are 10, or we can say minus 5 by 3 ampere. Like this you can find out the second current, that is I3. We got one current here I1, we got I3. Now if I put the value of I1 and I3, then I will get I2. So let us put the values. Putting the values of I1 and I3 in equation 1, then I will get I1 equal to I2 plus I3. I1 we got 1 ampere, I2 we are going to find out, I3 just now we found out minus 5 by 3. So I2 will be 1 plus 5 by 3, transpose it, is 1, minus will become plus, 3 once 3 plus 5 is 8 by 3. Like this you can find out the current in all the branches of the circuit. Here I2 is the current that is flowing through this cell with potential difference 4 volt. Like this you can solve the numericals. Thank you for watching the video and stay tuned with LFI Educates. We'll again continue with the new topics in the next video. This is video number 6.